is Steve. Today I'm going to kind of split up talking. I'm going to do half on Tesla coils and then half on speaker design. What we have here basically is a high power radio frequency amplifier on the bottom here. And then this is what they call a Tesla resonator. The input source right now is a DVD player. We originally had a battery powered CD player, but because of all the interference this thing produces, it was actually killing the CD player. It wouldn't run with the Telsa coil running at the same time. There's two switches here. The first one, if you see two blue LEDs in the bottom there went on, that switches on all the diagnostic equipment, all the monitoring stuff. And then the second switch there will actually turn on the amplifier, so that'll turn on the coil. Back here. Based on how it's tuned, you can get more or less of an arc. It's pretty small right now. If you up the power, you can obviously get a longer arc. The way to think about it is, like the higher the voltage, the longer the arc is. So you can kind of determine how much voltage you got there just based on how long the arc is. Before I start the music, I got a demonstration here. Everyone's seen one of these. Question two. This is a 32 watt tube actually, so it's not full brightness, but and as you can see it's brighter towards there and it's not as bright towards here. As I move it away, it stays on longer. It takes a little bit more energy to start it up, and then once it's going, you can kind of maintain it a little longer. So. And this one is probably more familiar. This is just what they call a CFL. So, somewhere in there. That one part of the lights up. Very cool. Next thing I'll do is switch on the CD player. So this it's going to be pretty quiet, but if you listen carefully, you'll hear it. So originally this design had two fans blowing to cool it, but it kind of obscured the sound. So we put this massive heatsink on the bottom here, so you can run it without a fan and it's easier to hear the audio. So as you can hear, the bass isn't really that good, but the treble is really there. So. To give you an idea of the power level, that big transformer, the input power is about 200 watts. That's a 200 watt speaker right there. Not very efficient, as you can hear. So one of the other neat things, if you had like an infrared, a thermal camera on there, you could actually see a heat profile. I mean, it heats up to literally thousands of degrees right at the top of that coil. Because what it's doing is it's basically ionizing the air. If you look at just the right angle, you can kind of see heat waves coming off of it. So, I guess that concludes our demo. All right. I bet everyone has questions, right? The two obvious ones that I thought of: why is it making noise? How does it make noise? And then also, the first thing I showed you, why does the fluorescent tube light up? So those are kind of if you've never seen something like this before, who's seen it before?
Only in videos.
Only in videos, okay. Those are probably the two biggest questions people would have. But is there anything else? Any questions I could answer? Yeah?
Would it be possible to increase the power and then use like a Faraday's cage? Like have it actually...
Well, actually, that's what this is. So you can put this on top of here. The only thing is it changes the tuning. So before I came here today, I actually took it up to what's called a network analyzer, like a $10,000 piece of measurement equipment, and tune it precisely to exactly the right frequency. The Faraday cage is mostly for like protecting people from touching it, but the other part of your question, to increase the power, you could easily do like 6 times the power. That would be 1.2 kilowatts. You could easily get that from the wall. If you go anything beyond that, you're going to have to start doing like 240 volts, which would be like a dryer outlet or a stove outlet. If you want to go real nuts, you could do 480 volts and have like a huge 30 kilowatt, but this is a start. Any other questions?
How big would increasing the power make it louder?
Oh yeah, definitely. You'd have to change the coil design too. If you can see, the top of that coil is kind of burned, so if you have too much heat concentrated in one area, it can actually melt copper. One question?
So in that case, would different windings actually affect how it's tuned?
Yep. There's a couple different arrangements. I'll show in this presentation the different ways you can make the resonators. Tom, you got a question?
What can you do to get more bass response?
That's a good question. I mean, there's always bass response there, but it's just the treble is louder, so you might have to actually just bump the power up on everything and then knock down the treble a little bit to balance out with the bass. Like, this is really unknown. People don't know much about how to design these compared to like a normal speaker in an enclosure in a box or something. And there it's easy to change 2 numbers, which I'll show you in this presentation. So I guess the first question, how does it make noise? 4 basic things you need to understand are transistors, amplifiers, what's called amplitude modulation, and then resonance. How many electrical engineers do we have here? Almost everyone. Okay. How many musicians do we have here? Almost everyone again. Okay, perfect. Excuse me if some of this is a little basic. So what is a transistor? I'm sitting there in the morning thinking, well, how can I explain a transistor? Well, this works. Starting off with the sink, pretty basic concept, right? You turn it on, water flows. You have a little bit of input turning on the faucet, and then a whole lot of water flows, right? And it flows from, you can say the faucet is the source, and then it goes down to the drain. So let's look at a transistor. The handle that you turn on, that's what's called the gate in a transistor. And then there's also a drain and there's a source. If you notice the picture of the transistor, that's an N-channel MOSFET on the left there. If you notice, the arrow is pointing from drain to source, but the water in the sink flows from source to drain. So if you make the analogy between the sink, you have water flowing, and the transistor, you have current flowing. Does anyone know why that arrow is backwards? Exactly, yeah. Electrons are flowing in addition to the arrow, but current flow is the opposite of that. So you have your basic building block, you have a transistor. How do you do something useful with that? What do you want to do? You want to turn it into an amplifier, right? So this is a really basic inverting amplifier. So if you notice, the faucet, it's easy to understand how you control it, right? You just move it. The transistor, there's different ways. You can either apply voltages or you can apply currents. In this case, you're going to apply voltages. So on the gate, you'll apply a voltage between, say, 0 and 5 volts. And then from the drain to source, you see you have that 100-volt power supply. So the basic idea of an amplifier is you have a really small, low-power input, and it's controlling a much larger, higher power output. So in this case, the transistor, you can think of it as a variable resistor. When you turn it on, when you apply a 5-volt signal to the gate, the transistor turns on and it's a short circuit. The other way around, if you apply 0 volts, it's off and it's an open circuit, it's a high resistance. And so basically what you're doing is you're directing the current between the load and between here. For example, when this is a short circuit, if the current's going along this direction, and it splits, which way is it going to go if this is a short circuit? It's gonna go here, right? It's gonna bypass the load. 5 volts, it's on, it's a short circuit, you're bypassing the load. So you have a voltage here, and you have no voltage here. That makes sense? So that's the whole inverting part. The flip side of that, the opposite way, if you have 0 volts, it's an open circuit, right? And so you follow the current along and it goes through the load and you have voltage then. Instead of having a DC power supply at the source there, what you can actually do is apply a sine wave. And then essentially what you're doing with an amplifier is you're converting DC signal from the power supply to an AC signal at the output of the amplifier. So resonance, all the musicians out there, you've experienced resonance if you're playing say a guitar or a snare drum or something, or a French horn. You play specific notes and it gets really loud, right? Something vibrates or resonates, or it just makes a lot more noise at one specific frequency, right? So that's actually the same concept that's going on here. That coil itself is tuned to resonate almost exactly 4 megahertz. So what this plot here is showing, this is what we call return loss. If you've taken senior electrical engineering class, 404, 405, along those lines, you've probably seen this before. If you haven't, the basic idea is this is your reference level right here, your 0 dB level. And when the purple line there is at that level, that means all the power that you're putting into the resonator, it's all coming back. So you're not putting actually any power into it, it's not accepting anything. And then that point right in the middle, that's right at 4 megahertz. When it drops down to, that's like negative 30 dB there, that means that the resonator is accepting all the power. And you end up getting a lot higher signal at that one specific frequency. Right before 7 o'clock, Mike and I were actually in the 405 lab, and we're sitting there, let's see, unplug it now. You want to let it sit for maybe a minute or two before you touch it, because there's a capacitor in there that has to discharge. But basically what you can do is you can play around with the height of that little loop on the top there, and that'll effectively change the capacitance of the resonator. And you can very finely tune the resonance frequency. And then the fourth concept is amplitude modulation. So the basic inverting amplifier, we were turning a DC voltage from the power supply into an AC voltage, the output of the amplifier. Amplitude modulation, you're essentially taking that sine wave and then modulating it again. So in this Telsa Coil Speaker, what's called the carrier frequency, that higher frequency signal in the red line, the AM plot, is 4 megahertz. So it's in the radio frequency range. It's something you would never hear. And then the modulation, the slow rising and falling of that 4 megahertz signal, that is the audio frequency. So between, say, 20 hertz and 20 kilohertz, much lower. And it's also something that you can hear. AM radio, it's the exact same thing, except here you're turning on and off a Telsa coil instead of turning on and off a radio transmitter. So here's a basic picture of what's going on in the Telsa coil. So at the very top there, you have the highest voltage, and then that little gold sheet at the bottom, that's actually ground reference. So at the bottom, you have 0 volts. At the very top, you have, I don't know, 500,000 volts or something ridiculous. And so in between, you have voltage, right? You have a potential difference. And so anytime you have differences in voltage, you have electric field. You have like field lines, right? You can kind of draw it in, and you can see, okay, it's going to be radiating electromagnetic energy. So when I took that fluorescent tube up to the coil and it lit, that's what was going on. It's actually transmitting energy wirelessly. Nikola Tesla, that was one of his big things he was trying to promote. 2 problems with it though. The first thing is power companies, consumers, DTE, Board of Water and Light, they can't charge you for it. I mean, if they're just broadcasting energy wirelessly, how are they going to know how much you're using? So nobody can make any money off of it. That's problem number 1. Problem number 2, it's very inefficient, because if you have, say, 100 watts at the very center of the Telsa coil, as it spreads out, it's basically like, has anyone seen those Lego, or not Lego, but like Connect Small, expand them and contract? You're taking the same amount of energy and you're spreading it out over a much wider distance. So essentially, if you're here, you get a lot less energy if you're here. So it falls off very quickly in terms of how much energy you're able to receive. You can also think, how can I make this thing louder, right? If it's radiating out all this EM, it's probably not being very efficient. So is there a way that you kind of concentrate those field lines to get a more focused Tesla coil arc. And so this is actually what's called a single-ended Tesla resonator. What you can also do is make a differential, like a dual-sided Tesla resonator. So if you compare the two, you're basically taking the same thing and you're mirroring it, doing it one more time. In this case, you had 0 volts at the bottom, you had 500,000 volts at the top. Here, you're going to have, if you have the same voltages, the same amplifier, the same driving electronics, you would have, say, like 250,000 volts on one side and then negative 250,000 volts on the other side. And in between, like at the very center of the coil, you'd have a virtual ground. So you'd have kind of like 0 volts, but not really. So this, if you kind of think of field lines and what they might look like, it would be a lot more concentrated. So this is the next step for this project, is to build one of these differential resonators and maybe get a little more sound out of it. It won't be able to probably light a fluorescent light as efficiently, but it should make more sound, which is what we're going for. Okay, so I'm kind of going to switch gears here and talk about speaker design. Everything from this point on, I'm talking about like conventional speaker design, so a speaker in a box, basically. This whole process of designing speakers based on design parameters was kind of discovered in the 1960s and the 1970s. It was, I think, government-sponsored research at an Australian university, University of Sydney. It was two guys, Teal and Small. And if you look at any speaker driver datasheet today, you'll see what are called the Teal-Small parameters. Essentially what they discovered was that speaker design is really just filter design with one more parameter. So filter design, you're worried about performance, like the shape of the filter, and then also you're looking at cutoff frequencies. So those are your two main parameters for filter design. For speaker design, you add a third parameter in there, which is the volume of the enclosure, say, that the speaker is in. So real quick, just types of filters, all the electrical engineers have seen this many times. A low-pass filter at the top left there, frequencies down to 0 hertz, it passes, and then at a certain cutoff frequency, it doesn't pass anything anymore. High pass, it's essentially the opposite of that. At low frequencies, it doesn't pass anything, and then once you go above the cutoff frequency, ideally it'll pass everything up until infinity hertz. And then the other two you have are a band pass and a band stop. So a band pass will pass one specific narrow band of frequencies and reject everything else, and then a band stop will pass everything and then reject one very narrow band of frequencies. Speaker design is one of these four. Does anyone have any thoughts about which one it would be? Band pass? Okay, that's one idea. What is it not? Which one do you eliminate right away? Which one? Did you hear band stop? Okay, that would be a little weird, right? A speaker that worked at every single frequency except for one? Yeah, probably not going to happen. Then also there's the low pass. Anyone seen a speaker that works at 0 hertz? No, me neither. So that one's out. So it's either we've got a high pass or we've got a band pass. And the assumption that Teal and Small made is that the design parameters are only valid for frequencies below 1 kilohertz. So basically what they're looking at is a high pass. The band pass isn't really relevant here. The high pass, they just assume it goes on, and above 1 kilohertz, it's just essentially the same as a tweeter. Speaker design is, in essence, high pass filter design. That's all we're looking at. These are the 6 parameters that you need to design speakers. On the left-hand side, we have what are called the driver parameters, and then on the right-hand side, we have the system parameters, so the completed speaker parameters. The driver parameters you will get out of the manufacturer's data sheet, and then the speaker parameters depend on the size, the volume of the box. The 2 frequencies, we have FS and we have FC. Those are what are called resonance frequencies. So if you look at this high pass filter on the top right there, frequency where it transitions from passing signals to not passing signals, that's the cutoff frequency. The Q of a filter, it's a dimensionless quantity. It's kind of hard to explain in words. I have pictures in the next slide that will explain it a lot better. The third one is the volume parameter. So VB is very simple. It's the volume of the enclosure. So if you have a box that's 12 inches by 12 inches by 12 inches, it'll be 1 cubic foot. The VAS, the volume for the driver, that's a little more obscure. So what they say is it's the equivalent acoustic compliance of the driver. It's kind of, you can think of it like a equivalent volume of air that the driver itself could be able to move. And the design process, pretty much all you're doing is the 3 parameters on the left, the driver parameters, you're given. And then 3 parameters on the right, you calculate. It's basically all there is to it. So Q, speaker Q, same thing as filter Q. So everyone who's taken 201 and 202, you all know what filter Q is. So the easy way to kind of visualize Q is you can look at frequency response, which is on the left there, and then time response, which is on the right. So these diagrams are actually straight out of the 1970s papers by Richard Small. You can see with the frequency response, if you want what's called a flat response speaker, can anyone see what Q value would be optimal? Ideas? You want it essentially to be flat until it starts to fall off. If you look on the lower end, like the 0.5 or the 0.7, the 0.7, it's essentially right flat at 0, and then it starts to drop off. If you have a Q of 2, you actually get an artificial bass boost. If your Q of your speaker is 2, at the resonance frequency, the bass is going to be 6 dB higher. You could think of that as though maybe that's a good thing, but then if you look at the time response on the right-hand side, take a look at the Q value of 2. Those are what are called impulse response diagrams. So essentially what you do is you start at 0 volts, you go up to 1, and then you go right back down to 0. You off, you turn it on for basically nothing, and then you turn it right off again, and you see what happens. In the ideal case, it would be a straight line, right? It would be off, you turn it on, you go right up, and then you would turn it off, and then it would go right down. In reality, what happens is, when you turn it off real quickly like that, if the Q is high, you get kind of like a holding over of the signal, so it kind of continues on when you don't want it to. So in speakers, that kind of shows up as what's considered muddy, like a very bad sounding, ill-defined speaker. I mean, it's not clear is the take-home message. About a Q of 0.7 is ideal for both filters and speaker design, so that's what you're shooting for. So the process is basically, you can simplify it to these 3 equations here. If we look back at here, we're given these 3 on the left there, Fs and QTS and VAS. So this first equation, we have Fs and we have QTS. So we're missing 2. If we want to solve that, we have to pick 1. The easy thing to do is you just set Q to 0.7, and then you have an equation with 3 known variables and 1 unknown. Right? So all you do is solve for the unknown. So that can give you Fc, and then the next equation, equation 2, you know Fc, you know Fs, so you do a little bit of algebra, and you can get alpha, and that'll be somewhere between, it can be between 0 and 1 or 2, I think, depending on what value you choose for Q. But then the third equation, you plug that in, and the VAS value. So if that is, say your VAS is 1 cubic foot, and your alpha is 2, then that would mean your box volume would be half of that. So you'd have half a cubic foot for your box volume. So it's kind of hard to see just based on these equations, but if you keep on doing all these speaker designs, you'll start to see trends, and you can kind of determine from the data sheet which driver would work best in a specific enclosure. For a speaker design, that's a take-home message, is that drivers and enclosures go together. So if you design an enclosure for a driver and you put a different driver in that enclosure, it's not going to work. Or if you change the box volume, it's not going to be the same performance. The speaker team for this semester, we're looking at designing a 6-sided subwoofer. So these are the drivers that we're looking at. And this is the exact same data sheet you would get from the manufacturer. You can see on the left we have all our teal small parameters. There's quite a few of them. All you really need are those 3 basic ones to be able to design speakers. First one I see is Fs, so that's 31 hertz. QTS we have 0.39 hertz. And then finally our VAS is 38.2 liters. I'm not sure why they do that. In the real world, we design with cubic feet. It's easy to take a volume in cubic feet and then design dimension. Liters, it's more difficult to do that. But all you have to do is convert between liters and cubic feet, and then that makes the design a lot simpler. If you're making a subwoofer, you can just make it a cube with all 3 sides the same. You go through the 3 steps, you do all your calculations, you get the box volume in cubic feet. You take the cube root of that, and that's the interior dimension of your subwoofer. It's as simple as that. The last meeting, actually, we were kind of trying out a few different Q values. We had one person do 0.7, another did 0.5, somebody else did 1, and then the 4th person did 2, and we kind of compared the performance of each design, like what's the box volume going to be, what's the resonance frequency of the system going to be, and kind of came to some conclusions about, is our design going to work, and is it viable? Picture that Jacob drew up a conceptual design of our 6-sided subwoofer. Plan is to have this done by the end of the semester so we can show it off at design day. The equations are going to be a little bit more complex, I think, than if you were to just have one driver and one box. The other thing we can do is just build it and then measure the performance of it and work backwards and see if the equations work out. To my knowledge, no one has ever done anything like this, so it'd be pretty neat, I think. And yeah, that's it.